So last time we talked about, and this is not on the test, I just want to point out that, actually I'm kind of confused, there we go. If we're back in the 1600s, and remember we're going to cover things learned from the 1600s to about 1880 in this class. Back in the day in 1600 they had balloons made of leather, so I'm sure they actually visibly resembled the parts of a cow. We know that if you define volume as V naught and another at T equals 0, and then if you have V100 at T equals 100, and this is water, freezing and boiling, that what you find is that volume, which cannot be below 0, you get this line, and we all know that there's no such thing as negative volume, and anyway, so you find that there's a temperature below which you cannot go. So recall that this was I'm just reviewing, this is a phenomenological model that we covered last time. 1600s, they now have balloons, they know about lines, they know how to fit lines with 2 data points. Hey, that's great, they're just basically making thermometers for the first time, but they kept seeing this weird behavior, and they know, there's no negative volumes, there's no negative pressures. You can have negative things, you can have negative velocities, you can go backwards. Back in the day, they could ride their horse backward after too much meat, and I'm sure they did. And you see the favorite that just came out?
Yes.
God, that disturbed me, that ending. Anyway, so lots of meat drinking in the favorite. But so they know, yeah, there's some things that you can, you can't have negative volume. So they figure out that there's an absolute temperature scale. They know that this also allows you to figure out things like what is temperature? Well, what can you do more and not less of, right? So this allows you to figure out things like from these phenomenological models that temperature is actually a form of kinetic energy. So you can imagine, I have a piston full of gas. I'm going to do this every time. And if I'm touching the sides and it's hot, it's because the atoms in the walls of the piston are moving, right? They're vibrating, and that's what I interpret as heat. And it also allows me to talk like this. And so that means that when the atoms are no longer moving, that you can't do less of that, right? And so that's why there's that at that point you've hit zero temperature, no more temperature decrease, because you can't not move less, right? And that doesn't even come out right, but why should it? Because right, there's no such thing as you can't move less than not at all. All right, so here's another phenomenological model, and this is going to be for pressure, which you know as force per unit area. Again, I don't think this will be on the test, but I'm just trying to get the point across about how phenomenological models work and how you can use them to figure out new things beyond what the model is meant to describe. This little description we're going to just spend about 5 minutes on. What I like about this is it actually reveals what the whole freaking point of this class is, which is that we're going to take information from a cow head balloon, as screwed up as that is, and we're going to figure out things about molecules. So, and then you can imagine I'm actually going to work the reverse this time. I'm going to take a model for pressure and work out the temperature or volume of a cow head balloon. The point is that I can take something as crude and basic as a cow head balloon, the pressure, volume, and temperature therein, and figure out some really minute detail about a molecule. And that's a hell of a thing, right? Especially back in 1600, when they weren't really even sure that there were molecules. In fact, they didn't really know that till 1800. Okay, anyway, so blah, blah, blah. So pressure, what is pressure? Again, a model for pressure, and as usual, I told you that everything's going to be in a piston or a box. And as about 2 weeks from now, sometimes the box will be wrapped in glass wool, sometimes it isn't. Okay, regardless, the box is L by L length. And I have an atom in there, let's say it's argon, and it's going to hit the wall and bounce back. Okay, now again, I'm going to do this kind of in reverse. I'm going to assume that molecules exist and that they have properties and that they're doing things, and those things manifest themselves in the macroscopic that are very easy to measure, like in Pekin lab or back when you were in high school or whatnot. Okay, now again, I'm touching the magic cylinder, and I know that the pressure inside of it is due to atoms hitting the walls, and so like if I'm trying to push it up and down on the plunger. That's what's fighting for or against me. And let's see, what can I do with this? So I know that pressure is force per unit area. And so what I'm going to do is try to figure out the force. Area is easy, that's L squared. But so the force, what's the force? Okay, it turns out that I remember my first semester physics pretty well. So you're going to have to hold on for a second. I'm going to start working some derivations, remembering what force is from physics 1. Maybe you don't recall, which is fine. But what I'm going to try to do is get to a change in momentum. Now, that's because I know that I can relate force to momentum. I bet you don't remember these equations, which is fine. Okay, the way I've drawn it, the velocity, the final velocity, I'll call it a little curly, little lowercase v. Maybe you're having trouble seeing it. Tell me if you're having some trouble seeing at the top. So I'll use a little lowercase curly v, so it's not volume, it's velocity. I can see that it ends at velocity, at a certain velocity. It started out with a certain minus velocity, so there's my change in velocity. Multiply the whole thing by m, and that gives me momentum. Momentum times the change in velocity is the change in momentum, so that's 2mv. I'm sorry, my handwriting still, it just takes me a few days. My handwriting will get much better. Okay, so again, I can see that my final velocity was v, my initial velocity was going the other way, is minus v. Again, this is all crude, I'm not worried about angles. That's what phenomenological models are kind of cool for. How long did it take to do this? Well, I know that so I'm working with velocity, and velocity is distance over time, so I'm going to have 1 over velocity because that's going to give me the right units of time. Then let's see, I have to then multiply distance over time, so I'm going to have distance on top. And I can imagine that the longest that this thing could travel in any given period of time would be 2L before it hits the wall. Remember, I'm talking about hitting a wall. So that's why I'm going to use 2L for time, because that's the longest it could ever travel before it absolutely hit the wall. It has to hit the wall over that length scale, divided by velocity, if that's the time scale. All right, so what about that? Okay, here's the thing you don't maybe remember from mechanics, which is force is mass times velocity, but that ends up being, well, here, I'll write that down. Mass times acceleration. Acceleration is a change in velocity over a change in time. M delta V is my change in momentum. So again, I happen to remember this from mechanics, that force is the change in momentum over the change in time. Oh, look at that, I've got the change in momentum, 2mv. M is the mass. Now this will get confusing, there's only so many letters, and so M is mass question.
How do you get the longest can go as 2L? Should it be root 2L?
Again, let's not, the L. Well, yeah, I guess from corner to corner, right? Oh man, I'm not worried about that. This is not important, right? I'm not too worried about cosines or sines and any of that. It's just very crude models. And again, this is why we often call this the back of the envelope calculation when you're at grad school. When we have our second year exams, which decide whether we go on to our PhDs, they'll ask us a really crude question like this, and we're expected to do basically this type of analysis. Anyway, okay, so delta, the change in momentum is 2mv. Velocity, a little b is velocity. The change in time is a maximum of 2L v. And so what have I got? I've got mv squared over L. Okay, force over area. Over area is the pressure. So I'll call that capital P, and that is mv squared over L to the 3, which is mv squared over the volume. And I'll write that out, VOL for volume, so you don't get the V's confused. Okay. Okay, so that's it. You don't care, do you? You don't see it, do you? Okay, check this out. So this is an aside. When I do that, that's an aside. Therefore, P times volume is mv squared. What are the units of mv squared?
kg meter square per second square.
A kilogram meter squared per second squared. What's that also known as?
Newton.
Not a Newton, a
Joule.
joule. So you're missing the half. 1/2 mv squared is what kind of energy? Who cares? It's energy. Right. You see what we just did? I mean, we just did this little model. But more importantly, I just showed you that pressure times volume is energy. I never thought about that before. And I bet you didn't think about that when you were in high school and you were doing this. Writing down a bunch of questions because again, you were very young, you were 16 or so. Pressure times volume is nRT. Okay, so we are going to spend today on PV equals nRT, and yes, it is very boring. I promise we're going to get to E equals mc squared in about 9 months. All right, but so this is actually almost a statement of the first law. This is not how the first law was discovered, which I will talk about, but pressure times volume is energy. So energy is constant. It can only change. It can only change this way. So in many ways, PV equals nRT. If PV is energy, and I just showed you is energy by this phenomenological model, yeah, I mean, it shows you that it can only basically take one form or another, but it can't be destroyed. It's basically constant. Now, another reason to bring this up, this is really all there was to this. Again, I just want to get to the point that we can learn macroscopic things from microscopic pictures. And again, that's really the whole point of this course. Okay, there's another part of this other than maybe pointing out that PV is energy and that energy cannot be created or destroyed, which we're going to go into a lot more a little bit later, which is units. So as I mentioned, as I beat to death, I unfortunately do tend to teach the test. And although this is important no matter what, whether it's on the test or not, which it is that you have to get your units straight. And unfortunately, in physics and chemistry, and this is the blend of both, we have units for everything. And you've got to get this straight. I'm also worried about your MCATs. A couple of MCAT people, yeah, I saw a couple. So let's see, what do I want to say about units? Well, let's do pressure. So pressure is, pressure has main units, but in SI it's a Pascal. So remember that, PA is Pascal. That is a Newton, force is in newtons. Per area, which is going to be meters squared, because length in SI is a meter. Notice that, I don't know if this is really true or not, but I can't but help but notice a couple of things. A meter is about the size of my waist. A liter is about how much water I would like to carry. Notice that there's a lot of sensibility to a human in terms of what we use as units. Kilogram, that's kind of heavy. I wouldn't want to hold much more than a couple of kilograms. So that ends up being a kilogram meters.
Per meter second squared.
Meter second squared, meter squared, which is a kilogram per meter second squared. Okay, and then when multiplied by volume, which is in meters cubed, you would get a joule. So there you go. Let's see, now you also know that pressure. Okay, here's the thing. I'm really tempted, and I did this in the textbook, to stick to SI units. I have almost universally written volume as meters cubed, although I do slip into liters sometimes. However, I know on standardized exams, God forbid if you want to go to grad school and you take the chemistry GRE, one of the things you're expected to do is be familiar with the different types of units we have, which is stupid, because, I mean, it's just like this exercise in useless memorization, but society considers it important, so do I. I don't, but you have to know this stuff. So anyway, so pressure can also be in ATMs. So let's say that 1 ATM. An ATM is kind of obvious. It's the pressure at beach level, but we all don't live, well, let me remind you that's also the same thing as 760 torr, which is also a millimeter of mercury, because as I allude in the book, back in the day, they used mercury manometers for everything, so that's your atmospheric pressure in torr or millimeter mercury. This happens to be, okay, in kilopascals, which is what I universally use, 101.325 kPa. You probably kind of have that number somewhat memorized, or you'll be very familiar with it in the class. Okay, where it gets a little funky is that 100 kilopascal is 1 bar. So a bar is slightly less than an atmosphere, slightly, like 1% less than an atmosphere, which makes sense that most people don't live right on the beach, they live slightly away from it, where the pressure is slightly less. Now the reason I'm bringing this up is I don't do too many questions with bars, but when we get to chapter 6, at the end of chapter 6, when we do chemical reactions in the gas phase, everything is in bars. So I do want you to don't memorize that, but don't forget it either. So I don't know how you can do both. Good luck with that. I also want to point out that the way that these questions work, and again, I do want to train you to do the best you can on standardized tests or whatever things that people tend to throw at you. Note that most questions in PChem, again, whether you're taking the MCAT or a standardized test, they tend to give you units, maybe like in ATMs or bars, so convert it to something you know works, like SI, and I tend to always do this, like I do the example problems in the book. I tend to use kilopascals for pressure, I tend to use liters for volume. Neither is standard SI, but you always see them multiplied by each other. One is 100 times too small, the other is 100 times too big, so they cancel each other out. So again, when you are doing PV equals nRT questions or some of the harder ones, pick a set of units and don't screw it up. Kilopascals, liters is what I would recommend. Moles is always in moles. Temperature is always in Kelvin. I swear to God, I will see some of you occasionally using Celsius for temperature. Oh, don't do that. What? You can't tell what I said. But anyway, all right, so talking about PV equals nRT. I know this is kind of like some of you are like, I don't remember this was 16. Yeah, I know. But so the thing is that, remember I told you that we're going to do a gas expands, a gas contracts, and a magic piston. And it's a stand-in. We're going to understand the thermodynamics of that because it's our route to understanding the thermodynamics of actual chemical reactions. So it's the stupidest, simplest chemical reaction. A gas expands, a gas contracts is an example of a chemical reaction, just a stupid, very simple one, but that's good. We will go on to do much harder ones. And so we're going to do PV equals nRT questions a lot with the magic piston because it's a gas and it's a piston. Okay, so when it comes to the things that go into PV equals nRT, those are state variables. And this is my backup pen, by the way. My real pen seemed to have died, so next time I'll make sure I have a nice dark pen. I know so everybody can see. State variables are, whatever. They I even talked about it last time. N and T and P and V. Okay, so there's 4 of them. Moles, pressure, temperature, volume, gas constant doesn't count. It's not a variable, it's a constant. I'll say a little bit more about that in a little bit. The reason we have all these is, it's kind of a little mind-boggling to think about this. I actually had my PhD was in molecular simulation, so I did some programming and whatnot. And I know that if you want to simulate a cow head balloon, your typical balloon would have about 0.1 mole in it, on the order of about 0.1 mole. And so 0.1 mole is approximately, again, I'll often be very approximate, about 10 to the 23 molecules. And if I wanted to do a simulation on a computer, I need 10 to the 23 memory spaces for that. I need to know where the atoms are and how fast they're going. So that's actually 6 bits of information for 10 to the 23 different pieces. Computer can't do that. I think a lot of engineers in here, right? A computer can't even get close to that. Maybe 10 to the 9 or something, but not 10 to the 23. That's ridiculous. Now let's say that it takes a computer 1 second to process that. Okay, well the thing is that a good computer is about 2.5, say, gigahertz. I notice that hasn't changed. I know multiple processors, some are a little faster, some are a little slower, whatever. They're around a couple of gigahertz, right? Okay, so if I have this computer working on that number, it still takes to do, to say, simulate motion with this number of information. It takes 0.01% the age of the universe to do that simulation, right? So to understand my cowhead balloon with the computer by simulating all the positions and velocities, it reasonably takes a sizable fraction of the age of the universe to simulate something that I really don't give a damn about. With state variables, this 10 to the 23 turns into 4. What I lose is, technically the proper word, if you go on to get a PhD, which you absolutely should, the proper word is course grading. So I'm taking all this information, which is the correct information I really need, and I'm saying that for all practical purposes, I can reduce it to these 4, and I effectively know what I need to know for the magic piston to drive the car, to drive you to work, to get a PhD, and that's why we're here. So, anyway, so that's the importance of state variables. What do you do with them? Here's a little bit of a history lesson. I actually did try to cover a little bit of history in this class because some of it's kind of funny. Some of the people who, like Gibbs was completely boring. He lived and died at a university. That was boring. His father was portrayed by Matthew McConaughey. And Amistad, have you seen Amistad, the movie? Actually, Matthew McConaughey wasn't Gibbs' father. Gibbs' father was one of the lawyers on the Amistad trial. I'll talk about that when we talk about Gibbs. So some of these guys were kind of cool. So let me go over historically how some of this came about, which is Boyle, Robert Boyle, 1600s, I told you we're starting in the 1600s, and Robert Boyle was the founder of the Royal Society, which is where we get our professional societies from. Actually, universities, they actually started from, you knew this, they started from monasteries, right? In fact, if you get a PhD, what you do is, you stand up in front of everybody, and I come up behind you with a rope. And I'm not joking, this is actually how it works. When you go to graduation, you'll actually see me, this is called a hooding. The person stands there, and my PhD graduates, and I have this thing that's kind of like a towel, and that's the hood, and I wrap it around their neck. Where that comes from is in the monastery, the people that we call PhDs now were the monks who were just writing, they just copied books. It got cold at night, and so they wrapped their necks around their hoods. So anyway, that's where we get that. Why am I talking? I forgot why I'm talking about this. Anyway, so Robert Boyle is, and I'm talking about this because Robert Boyle was the guy who started what we now know as a professional society, which was the Royal Society. And it was the Royal Society where a lot of the people we're going to talk about, James Joule coming up, where he presented his results, which led to the first law at the Royal Society. And anyway, so what he found was, I'm going to use, you have to get used to my notation here because I just can't write all this out. It's just too much, so you'll get used to this. What Boyle found was that given a certain mass, I'll say given N for moles, but given a certain mass and temperature, he found, that's a therefore, he found that PV is constant. Okay, so that's what he found back in 1600. I actually found a picture of his, I found his original report. I found a copy of his original report, obviously digitally archived, and I got permission to reproduce part of it in your book where I showed some of the actual instruments that he actually made. He drew a picture of some of the instrumentation. You can tell it was actually quite fine, about as good as what you have in freshman lab, probably slightly better. And so he was actually really quite accurate in these measurements back in 1600. So what about this? Well, now again, I want to agree that this will sometimes be a little boring, but I want to make sure that you're up on your calculus. And I even talked to a professional educator about how to do this. If you have problems with calculus, you're going to do very badly in this class. I don't think that's many of you, but if it is you, I do have a calculus tutorial on the website where I did this with just a review of calc. If you have problems with this, you need to unproblem yourself because this is calc-based. It's multivariable calc-based. So just in case you're having any trouble, I want to unstick you, and I also want to show you a type of question that I frequently ask throughout this course. Okay, so if P times V is a constant, then you should get this type of behavior, right? 1 over X type of behavior. Okay, again, this is high school, you know that. Let me ask you this. When I drew it this way, how is pressure changing? Now tell me, how do I write the change in pressure? Let me write it mathematically. Delta P. I tell you what, let's do a minuscule change, right? A minuscule change in pressure. So like lowercase Greek delta, right? Calc, right? I'm trying to do some calc. Change in P. Okay, change in P. When I drew pressure going this way, positive or negative? Negative. It went down. Okay, it went down as volume went what?
Increase.
Volume went up. Remember, there's no negative. You can have a negative change in volume. That's fine, but volume. But I drew it this way, right? Pressure and volume. The origin has to be 0, 0. It has to be 0, 0. Okay. So if the change in volume is positive, the change in volume is positive. I think I said that right. The change in volume is positive, and the change in pressure is negative. Okay, now what do you think dPdV is? Is it positive or negative? Negative. Right, dPdV is negative. So if I have an equation like PV equals nRT that has P and V in it, and I do the derivative of dPdV, I better get a negative quantity. Now again, that's not too hard for PV equals nRT, but you're going to do some much harder questions. If those of you who looked at your homework question, notice that the theoretical, the last two are kind of like 10 pages long. So there are other equations other than PV equals nRT for which you're going to do dPdV, and it's going to blow your head off. I'm actually going to tell you quite a bit more about how to do those questions in the second hour on Friday. So if you have looked at the homework question, you probably should do that. You absolutely should do that by Friday. And note that the theoretical questions, I am trying to get you used to doing derivations that span the page. You kind of need to be able to do that. It's not that bad. It's large but not complicated. Anyway, another reason I bring this up is that I frequently ask questions, is it positive, is it negative? Because it just tells you how things work. It's very easy. The second thing is, if I have you do a complicated question, and I have you do this on something complicated, and you get a positive, you did it wrong. It's a way to know you did something wrong. It is often universal. Well, no, did I say it's often universal? When I have people that work for me. What makes someone very useful from someone I'm going to let go? What makes one different from the other? The person who gets let go is someone who basically does whatever I ask. But that's not the point. Doing what someone asked you to do and everything's working fine, I have no idea what you can do. I just have no idea. The person that handles themselves in an accident, who ended themselves well when something's not right, when something's not working, the person who can take that situation and turn it around, that person's useful. So, again, if you do a derivation of dPdV, no matter what equation you use, if it's not negative, it's wrong. If you recognize that and fix it, you're useful, and I won't necessarily fire you. It depends on other things. No, just kidding. So look out for that, and yeah. So anyway, I'm still babbling. Let me go on from here. That's Boyle, and the next person that came along was Charles. Let's see, who is this guy? Jacques Charles. So we have Boyle's law. We have Charles. My cat's name is Charlie. She's a girl. The person I adopted my cat, Charlie, thought she was a boy, so she named her Charlie. And I bring her over, I'm like, that cat's a girl. And she looked at me and said, how do you know? And I said, I'll take the cat. She should not be having the cat if she doesn't know if it's a boy or a girl. Anyway, so Charles was in the 1800s. So we've automatically shot 200 years in the future. This is how slow people actually are. That it took 200 years for Charles to come up with, given, let's see, I gotta remind, I never remember these, by the way. Given a certain mass and pressure, he figured out that volume is proportional to temperature. He also found that if you are given a certain mass and volume, that pressure is proportional to temperature. Okay, so this character actually was kind of cool. He figured out how to isolate hydrogen gas from the reaction of iron. They had tons of iron back then, and sulfuric acid. I'm not sure we got a hold of sulfuric acid. but if you take iron and sulfuric acid, you get hydrogen gas. So he actually filled a balloon with it. And so he absolutely did do this, him and a couple other people. And they don't know this because it was the 1800s, but they think he's the first person to ride in a hydrogen balloon. Didn't blow up, he got lucky. But he's the first person to ever, now think about that. Seriously, you know, like when you're in an airplane, or sometimes if you're just like, if you ever go climbing, you're high up, you know that's a hell of a thing. You don't even have to get that high, maybe 10 stories. And you're looking down, you're like, whoa, that's kind of cool. He's the first guy to do that. And being in the 1800s, apparently all the peasants freaked out and they thought he was the devil. And that's not a joke, it's on Wikipedia. They saw this, not a man, men don't fly, but here's this guy in the air. You got two options, angel or devil. They went with devil. So they started chasing after him. And he's smart enough that he knows he's not the devil or an angel, but he looks down and sees these guys chasing after him, and he figures out, oh God, I'm going to die. Because he was going to die. So I imagine he was like, again, the first guy in an air balloon, so he's, who knows what he's doing, right? He got lucky, and apparently the wind blew him away from the peasants fast enough that when the balloon crashed, he ran for it, and the townspeople got the balloon. Of course, they destroyed it because it's the devil. But he lived to tell the tale, and he's the first person to ride an air balloon, and that's how he figured all this out. I thought that was neat. Anyway, so you know, sorry, let me go back to Boyle. You know that this is technically an isotherm. So now that I have Charles, I can show you, let's see, a V versus T diagram, and you know that that's actually rather boring. It should be linear. And this would be an isobar, right? So there's that bar notation. That means that it's at a single pressure. I actually did, for your book, I really did try to make graphs in 3 dimensions because I think that looks cool and I'm good at that. I can't exactly do that here for obvious reasons. But there you go. Now if I see that if, how is volume changing? Is that what? You know how to play this game? It's incredibly simple. Positive. And that's of course if the change in temperature is positive, therefore dV dt. When I have my calculus done correctly, I better get dV as positive. So there you go. Okay, all right, let's play this stupid game. All right, okay, I could draw 2 different isobars. There's the second isobar. Which one? I've got V changing, T changing, therefore P has to be constant. And I've already said that, it's an isobar. If I have 2 different lines, they have to have 2 different pressures. Which one's higher pressure and which one's lower pressure? What do you think? High pressure or low pressure?
High pressure.
High pressure. Low pressure? High pressure. All right, okay, very good. High pressure because the volume is, there's less volume. And of course, a less volume means higher pressure. Wait, is that right? I better go with, yeah, that's right. So there you go. You can imagine I could put that question on an exam, and you actually, most classes, now you're kind of good. Most classes actually about half the class, they're not really thinking, but they get it wrong. But anyway. Now here's a good one, P versus T. Again, it's just a line, but I bet you haven't heard of this before. This is called an isochord. Yeah, isochord. Okay, well, since you got that, high or low? Okay, this one. High volume or low volume?
High volume.
Gotta remember. Yeah. I know. I can read. So anyway, yeah, I had to think about it, right. Large volume means low pressure. I had to think about it myself, so there you go. Okay, yeah, I've got 10 minutes left, so I can just cover 1 or 2 more things. And more things about units. So I often do have questions on the exam about units. And one reason is that I do find that, okay, I told you a little bit about answering questions. It is important to recognize when you make a mistake and to fix it. And I emphasize that. Sometimes I have on homeworks and exams, I've given you an example problem that's wrong, and I have you try to figure out why it's wrong. Right? You see why I do that? Because you really have to understand this stuff to get that right, to fix or wrong. It just tests your ability in a way that I think just asking a P equals N or Q question doesn't. So one way to know, I talked about dP dV. Another way to know what the heck is going on if you're lost on a question or if you're not sure you did it right is to do a unit analysis. So let's put all this jazz together. Let's put Boyle's law, Charles's law, Avogadro. Avogadro said that, I'm not going to write that down because it's boring. Avogadro said volume's proportional to moles. Actually, no, this is kind of neat. Actually, I should write this down. I should write this down because it's kind of neat. So Avogadro, better learn how to spell it. Okay, Avogadro doesn't get a law. So that was Charles's law, Boyle's law. Avogadro gets a hypothesis. And the reason is that, according to philosophers, I suppose, molecules are theoretical because you cannot see them. So, with your own eyes. So he doesn't get a law, he gets a hypothesis. And his hypothesis is that V is proportional to the number of moles. So, and he was, so who was he? He was actually, so this is around 1811. So, hey, we're getting along pretty well. Remember, we're going to get up to about 1885 or so. And he was a political pundit. I'm glad he's dead. Anyway, so that was dark. So if we put these together, all right, so we know that from Boyle that PV is proportional to something. From Charles, that P and V were both proportional to T. And if we throw Avogadro in there, we also know it's proportional to N, so they have to be on opposite sides of the equation. And I've drawn proportional because as I was just blabbering there for the longest time and harking back to the beginning of this class, I know that PV and proper SI units is going to be in a kilogram meter squared per second squared, which is a joule. That's a joule. Okay. N in T is a mole Kelvin, which is not a joule. Something is wrong. These are not equal. This equation is completely incorrect because the units have to match. Units on either side of an equal sign have to have the same units. And the clever thing is, and I'll write this out as it's traditionally written out, is to insert something that just makes it work. Where R is the gas constant, and since I'm in SI, that's 8.314 joules per K mole. So notice that wipes out the, in a unit analysis, that wipes out the moles and kelvins and leaves joules. Now I got joules equals joules, and you better have an equation. Left side has a unit, right side has a unit. They better be the same unit. If they are not the same unit, something is wrong. Again, another way for you to analyze your homework and test questions in case you're like, I don't know what's going on, I don't know what's being asked, I don't know if I did it right. Do a unit analysis. Make sure the units work. Again, whatever on the left, I said, hey, what's the pressure of blah, blah, blah? Blah, 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 better have pascals. It better be a kilogram per meter per second squared. If it is not, you have done it wrong. Hey, if you've gone that far, then you're probably going to be able to get it right. Or you could even tell me, you know what, extra credit. Tell me, you know what, I've done this wrong, the units are wrong. Hey, you know what, I'll give you a point for that. Because that's, again, you're being useful. That's a good skill to know when you've done something wrong. I appreciate it. Okay, now there's one thing that's kind of cool. The reason I bring this up is, now I'm harking back again to teaching to the test, do the homeworks. When you guys screw these questions up, P equals NRT, seriously, P equals NRT, you're going to screw them up. Some people do because you use bars or atmospheres and 8.314 for the gas constant. That does not work. This gas constant, this particular gas constant is in SI, so you better be using pascals and meters cubed or kilopascals and liters, which is 1/1000th of that. So anyway, just that's how people tend to screw this up. That's one way to know you screwed it up. Now there's another neat thing about this. I'm not going to bring this up again in this class, or maybe even 346 if I teach 346. It depends whether I like you or not, or if you want to get rid of me. It turns out that you see that what I've done with this gas constant is it's been used to translate the units into something that works, right? Well, the thing is that if I did not have units, if my definition of units were such that length weren't about the size of my hip, if a liter wasn't about the size of a jug of water that I'm comfortable carrying, let's say that we use units that are more natural to nature, not natural to me, but to nature, then there are no constants. The constants would be the number one. So if we had a completely different, well, I can tell you that if we use nanometers for length, if we use 2 times 10 to the minus 17 seconds for seconds, if we use Hartrees for joules, anyway, okay, I'm going down a rabbit hole. But if we had a different set of units, every constant you've ever run into would be the number 1, meaning that there are no constants. Take, for example, one really annoying one for Coulomb's law. The one over, don't write this down, don't write this down, I'm just saying stuff, it's just kind of neat. You know that one over the square root of 4 pi E naught permittivity of space that appears in Coulomb's law? It's really annoying. Use the right units, it's 1. So anyway, the reason that we have all these constants in all of our equations is because we're not using the right set of units. But we have to use the units that are on your MCAT, so our state's good. Anyway, it's just something I wanted to point out about units. Last bit, and I know I've got 1 minute, right? You got 1 minute? Okay, I just want to point out Dalton's law, because this is going to come up in chapter 6 when we actually get to chemical reactions. Dalton's law. So when we do chemical reactions, and we're going to do gas-phase chemical reactions because that's like way easier, I just want to point out that we're just going to exploit the perfect law and say that the pressure, when you have more than one gas, is going to be equal to the sum of mole fractions of those constituent gases, where a mole fraction, of course, will be the number of moles of gas A over the total number of moles. So, sorry, handwriting is not nice, so my handwriting is getting slightly better even as I'm writing. Anyway, so this is Dalton's law, and therefore the total pressure can be the sum of the constituent partial pressures. Now again, this is at the high school level saying, but we are going to use this heavily when we do gases react, because A is going to be reacting with B, which is going to react with C, and that's going to change the partial pressures. You don't have to memorize this, but we will get to this in chapter 6. There's another neat thing that this will come up in some of the questions I asked for this chapter. And I want to show you how we're going to use PV equals nRT. I can give you this, and I can say turn this into pressure. Give me mole fraction as a function of pressure. What you do is you insert PV equals nRT, right? So what you do is solve PV equals nRT for number of moles of A, and what you get is PA volume. Now they're in the same container, so they would have the same volume and the same temperature, and then divided by the total, which would just be big P. Again, it's the same volume, same R, same temperature. And then what you find is all the V's and R's and T's cancel, so that a mole fraction can be described as the partial pressure divided by the total pressure. Again, the point of this is that as much as a mole fraction is brainless, of course you know what that is, this is child's play, but we can do some clever tricks and turn these into other units by manipulation of PV equals nRT, and we're going to do this a lot as we move into chapter 2. So anyway, okay, I'm not over.